Hello everyone, my name is Sam Biddlecom. I am the Motion Product Specialist here at EandM, and today I'm going to be doing a little update video on TA Selection Tool. The user interface has changed dramatically in how TA Selection Tool works. This is a free software um, with free updates that Siemens offers for configuring all sorts of hardware from Siemens, but particularly today I'm going to be focusing on configuring a servo drive system and kind of the day-to-day use I get out of Selection Tool and how nice and convenient it is. So to start, um, I have it set where my Selection Tool opens up to the project view of the system. If you ever want, it usually starts on the portal view, but if you never need to change it in between the two, we have this bottom left from our project window here. You can just click on that to go to project view or portal view or to project view as seen. So once in project view, we have our first group that we're kind of making all our changes and devices in. All of our axes, motors, frequency converter tabs that we're going to make today are going to have this properties window. It'll have the group name, it'll have the name that we can change, who the editor is, me, for example, the application, notes you might have, and it has timestamps for both creation and any changes made. So the first thing we're going to want to do is add a new device. You can either do that by double clicking in the project window or right here. These informational buttons give you the information on exactly what the software, your controllers, I/O systems, HMI panels, for example, might be, or in our case, drive technology, which we are going to click on today. And we're going to go with drive dimensioning with Sizer integrated in the TA selection tool. Do note Sizer is the old sizing software that Siemens had for drives and motors and whatnot. That has been phased out and now fully integrated into selection tool with the full range of drives, including the newer drives as well that are coming out. So we're going to click on this first option. From here, in our work window, we're going to have multiple tabs up in the top, and we're going to default to portfolio section. Do note now in our project tree, we have an undefined axis that we've added. That's perfectly okay. I'm going to kind of go through these tabs before coming back to portfolio selection to make my choices. But in properties, that same properties tab we talked about with group one, in load distribution, we're going to keep it on a one-to-one, one motor connected to one frequency drive load distribution. However, you can split this up to group drive and gantry type systems. In this motion control tab, this is where you'd have any assigned controllers for motion control activities, and then cabling, which we will come back to at the end. You can either size it in our project window, which I will be doing later on, or you can size it from this tab by selecting the axis. Both ways valid, but we'll get to sizing cables a little later on. So for our portfolio section, in our work window, we're going to start defining a lot of our options here. And from here, it will limit what our possible solutions are over here, which shows all our motors and drives applicable. Do note when I'm kind of scrolling over this highlighted section, it shows all the corresponding drives that can connect to the motor, and then also it can do the same vice versa below that we have. So I'm going to start putting some options in to size this out. So country of installation, I'm going to US installation, going to keep it at three-phase, 480 volts, 60 hertz. For today, I'm going to keep it at a single axis drive system that is cabinet mounted. Not going to worry about distributed mounting just yet today. Maybe in a future video, do explore these options for the G115D and G120D, or or well, not or, but definitely expand upon and do a multi-axis drive system. But I kind of just want to show the ins and outs of setting up your axis because then this just adds a little bit more hardware we need to spec out and connect to then add to our bill of materials to have this multi-axis system applicable. So I'm going to not change anything in installation or in motor. I'm going to keep it on servo motor today. And then gearbox, I'm going to keep it without a gearbox, even though we can choose between standard and planetary gearboxes. And then in our technology requirements, here is where we can specify our field bus interface, any sort of braking or regeneration needed, safety integrated functions, motion control requirements, and speed control. I'm just going to keep these all any, just keep our options wide open, but if you did have any specific preferences like Profinet, Profibus, ASI, or USS Modbus RTU serial connection, you do it here. And then underneath ambient conditions, I have our installation altitude and ambient temperatures, any sort of explosion protection. I'll just click on none, but here's where you define those. And last but not least, you definitely want to go underneath certificates, highlight UL-R/CSA for North American certifications. As you can see here, some of the options already went away, like that V70, which is not applicable in the States, which is exactly what we want. Now from here, we can move forward to adding our load. However, before we do that and we move from our Axis portfolio selection, do make sure in possible solutions to click on the motor and frequency converters you want to choose from. But of course, if you don't have any sort of preference on what material to use, you can click select all and just get the wide range of all products that might be able to fit the load and application requirements that you would set. Speaking of, let's do that now. We're going to go to add load. Here we have a bunch of mechanical systems laid out for us, as well as additional load types to choose from and loads for linear drives. I'm going to keep it simple and just stick with a sort of ball screw actuator mechanical system. I'm going to click OK. Do note when we add load, we have this folder that gets defined. Once again, it's just the properties of it, but then underneath, we have two configurable set points. We have our mechanical system and our motion profile. Starting with our mechanical system, same properties page, we're going to go to configure. This configure tab will be available for the motor and the drive as well to define whatever options we may have to define the motor and frequency converter. I'll kind of review those when we get there. But in our load section, we have this nice graphic of our ball screw actuator with a bunch of variables that are broken down on the right here underneath the various tabs. You can fill out all these tabs and get all this information if needed. You can be as detailed as you want, but to completely configure, quote unquote, um, the full system, all you have to do is answer the options highlighted in this orange. Here, these are the main variables that need to be defined to be able to configure your mechanical model. So in this case, we have a steady payload, which I'm going to say is just 20 kilograms today. We have a ball screw diameter. Let's say it is 10 millimeters. Ball screw length, 1,000 millimeters. If you know your ball screw density, great, you can put it in there. But this little table of contents button here opens up a lot of common materials that your actuator may be made of. For today, I'm going to go with steel. And then it punches in the ball screw density there. And then lead screw pitch, I'm going to put 3 millimeters. Once we enter in that final option, you'll see that now in our project window, it went from a hazard symbol to a green check mark. We have defined it. And of course, once again, you can add the other options if you have them, as well as transmission information if needed to further spec and define your mechanical model. Moving on though, we're going to go to our motion profile. So a motion profile, similar to the EMS configurator we did with Festo a while back, we have here kind of broken down our movements in steps. This is our forward direction, and then with this pin system, we can kind of pick and choose what three variables we want to basically edit and then fill out, and then we'll then fill out the rest and calculate. So with these pins, I like for today's, and what I usually like to do is how far are we moving this? RS. What amount of time do we want this to take to move? And then what type of motion are we looking for? I'm going to go to the trapezoidal figure here, basically defining a constant acceleration to speed point and then constant deceleration to stop when we turn it off. Once these are defined and we have our forward motion, we're going to first change this unit to millimeters because we have a millimeter system in our mechanical model. And I'm going to define, I want to move, let's say, 500 of the millimeters over 10 seconds. And then here, we can also change our units here to make more sense, like millimeters per second, 75 millimeters per second for our Vmax. And then our T pause will be our pause time in between our movement, or in between our moves. So in here, I'm just going to put a 2-second pause time. And we have a nice graph that's forming above. Now, we've just moved out our axis from our home position 500 millimeters. Let's do a full range of motion back in our second step back to home, so 500 meters in millimeters in the opposite direction. So to make sure we do the opposite direction, we want to make sure to flip this button. But first, instead of typing everything back over, I'm just going to click and highlight this top section, as can be seen here, and then Control C and Control V for paste. And then change my direction. Now our motion profile is complete. You'll always have this like nth move profile added after your last one. Perfectly okay. The system will still just look at your two moves here. And then as you can see, our motion profile in our project window was defined once we added our first move, but now we totally have our movement done. Now from here, with our mechanics and motion profile chosen, we can go forward with adding our motor and frequency converter. Starting with motor. Just going to click on motor here, and we see all the available motors below and the application requirements based off of our load properties that we had added up here. So in this case, we really have a very low torque and average speed that we really need to hit. This is something very easy that we can do in required effective power. So from here, we can either search up a motor if we have a motor name in mind from Siemens, or choose from the list below. All these values here kind of relate to the ones up here. So rated power, shaft height connection, rated maximum and static torques, rated speed, max speed, the number of poles in the motor. So from here, I'm just going to kind of go through, and I'm going to choose a 1F T2 motor. Once we kind of highlight and select, we'll see a torque versus speed chart on the right here, which is what we kind of use to size and make sure the motor is within our requirements. It's very much underneath our maximum torque line up here, as well as below our thermal limit, which is this red curve. This is our peak load point and our thermally relevant load point, so we are very much within the range of this motor. If anything, it might even be overkill. This is kind of the sweet spot we want to land in. We can go above this, but just do keep in mind, like, overheat issues you might have with the motor might shorten the lifespan of said motor. And of course, we want to stay underneath the black curve up here, which is our max torque. So to choose the motor, we would just highlight. You don't even have to highlight, but you would just double click. Once it gets added, it's up here. We see that our motor is now defined. All our options are in here. Now we can go on and add our frequency converter. Here in our frequency converter, we're going to be going with an S210. Pairs really nicely with the 1FT2, 1FK2 family. And do notice you might get these symbols on the right here just by hovering over it and just waiting a second. It'll bring up that this symbol means that our frequency converter rated current is greater than or equal to the motor stall current. This is actually a good reminder that we want this for our drive to the motor. So always try to look for that symbol and make sure to choose a drive with that symbol if you have symbols like this shown. If you have anything where the blue is on the top, be careful. You don't want to choose those. That could cause some issues down the line. So I'm just going to choose this first S210. It's kilowatt, reaches what we need, 1.2 amps above the motor stall current. We're good. Very low utilization or current utilization. And there we go. We've selected it. We have all green, so we have no issues. Motor stall current is less than the rated current of the drive, which is what we want. Perfect. And now, as you can see, we can go back to the Axis tab here to configure our cables. But once we configure everything, we can see navigate to cables is already an option in our project window. Here we will choose this. And because this is an S210 system, it is an OCC cable, so we only see our power connection available here. Usually, if it was any other type of motor, we'd see a blue line underneath defining our signal connection. So we just kind of click on Add Power Connection here. And then from here, you can kind of choose the minimum lengths for your basic cable. You can also go other options as well, like an extension, so on and so forth. So over here, 5 meters is fine. It shows your part number here. Click OK, and we've defined our cable. Last but not least, before we wrap up, nice little drive view. We kind of defined our mechanics and motion profile, motor, drive, right here. In our main circuit, nothing else there. Oh, there we go. Cable overview in our drive view. That's the cable we just spec'd. And then drive click topology is really nice. This just shows very simply our S210 drive, our our motor and the encoder that we're connected to in the power down here. Yep, motor encoder. Cable that's already there with our OCC, but if you up here, we can actually define even further our cabling. So we can click on this to generate standard cabling. From here, we could generate standard cabling. In this case, we only have the OCC, but for multi-drive systems, we might see this more in depth with our when we do a multi-drive setup and configuration. We would have more options down here, and just by highlighting this, we can see access to encoder and see this um, cable over it. We can't change the length because this signal cable is in the OCC, so it's already at the 5 meters. But in the future, we'll see maybe like a smart line module next to it with two other drives connected to motors. And down here, we could configure and add all of our drive click cables and signal cables accordingly in the system. And then last but not least, if you want to see what you have so far, you can go to your order list tab, and this will break down your full system, broken up into the separate tabs. Your motor with part numbers. Clicking the hyperlink will take you to SciPortal of each of the part numbers and each of the items. And then from here, you could export this to a PDF, an Excel file for easy use, and copy and paste features of the part numbers for quotation. And that is essentially setting up a very basic S210 servo system. You can do this in SBC also, but in future videos, I'll go more in depth on setting up of a multi-axis system. I hope to see you in the next one. Thank you for coming today and have a great rest of your day.